Today we are going to learn the first chapter of 10th standard chemistry. The chapter's name is periodic table and electronic configuration. A modern periodic table is given here. You can see from the table, it is all the elements are arranged in the increasing order of their atomic number. As you can see, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, etc. Likewise, there 1 not 3 elements are arranged in the increasing order of their atomic number. Atomic number is the basis of classification of elements in the periodic table. If you know the atomic number of an element, you can determine its position and nature from the periodic table. An example is given below. From the periodic table, we can see that atomic number of sodium is 11. Then we can calculate the group number and periodic number from its atomic number and electronic configuration. Electronic configuration is 281. The classification of periodic table is done in such a way that we can analyze and predict the properties of elements. Look at the picture given below. This is the Bohr atomic model of sodium atom. As we know, there are 11 electrons for a sodium atom, but it is arranged in different shells. According to Bohr model of atom, electrons in an atom are arranged in various shells around the nucleus, and they are filled in the increasing order of their energy. As the distance from the nucleus increases, the energy of the electrons in the shell increases and the attractive force between the nucleus and the electrons are decreasing. Got it? The first energy level which is lying to the nucleus is called K shell, and the shell number of the K shell is 1 because it is first shell. So, for the second energy level is called L shell and its shell number is 2. And for third energy level, the shell number is 3 and the name of the shell energy level is M. Next, the electronic configuration of lithium is 2-1 because there are 3 electrons in the lithium atom. Like we can calculate all other electronic configuration of all other elements. Here is some example is given below. You can see that atomic number of sodium is 11. So we can calculate the electronic configuration 281. And for argon, its atomic number is 18 and electronic configuration should be 288. And as you know, the first 2 electrons are lying in the kth shell and the shell number is 1, and the next 8 electrons are lying in the L shell, and the last 1 electron is lying in the M shell. For sodium, in case of argon, the first 2 electrons are lying in K shell and the second 8 electrons are lying in L shell, and the outermost shell includes 8 electrons. Now we are heading to a new topic called subshell. Before learning subshell, we have to know something that we have learned earlier. What are the energy levels? We learned that each electron in an atom is occupied in their energy levels. Am I correct? The electron in each level are arranged in its sub-energy levels. These sub-energy levels in a shell is called subshell. Then what is subshell? Subshells are the sub-energy levels in energy level. They are named as S, P, D, F respectively. S is for first sub-energy level, and P for second sub-energy level, and D for third sub-energy level, like F for fourth sub-energy level. Each main energy level except K shell has more than one subshell. The number of subshell in each energy level is equal to its shell number. K shell has only one subshell. Why? Look at the example given below, which is a hydrogen atom. There are only one electron in the outermost shell of the hydrogen atom, because hydrogen atom's atomic number is 1. So the only one electron is lying in the K energy level, and the only one electron is lying in the S subenergy level. In case of lithium, the first electronic energy level is K, and there are 2 electrons is lying in the K shell. So the all 2 electrons are lying in the S subshell of the K energy level. And look at the second energy level, which is called L energy level. There are only one electron which is lying in the S subshell of the L main energy level. Look at the first table. For kth shell, the shell number could be 1, because this is the first energy level, and the subshell should be S. There are only one subenergy level for the kth energy level. In case of L, the shell number should be 2, because L is the second energy level, and the subshell should be S and P. Look at this, S and P. There is no D or F. Only two subshells are here. For the third energy level M, the shell number should be 3, and the subshells could be S, P, D. There are 3 subshells. For the nth or fourth energy level N, shell number could be 4, and the subshell S, P, D, F. There are 4 subshells for the fourth energy level. There are 3 subshells for the third energy level. There are 2 subshells for the second energy level. There is only 1 subshell for the first energy level. A subshell is common to all shells. Let's give the serial number of the shell to the symbol of the subshell. For example, one has to indicate the A subshell of the first shell. Like 2p indicate the P subshell of the second orbital. More examples are given in the table. The shell numbers are given in the first row, and the subshell are given in the second row. Representation of the subshells are given in the third row. We can see that according to the shell number and the subshell, we can indicate the subshells as with their serial number. How many electrons can be filled in each sub-energy levels? Here we are going to learn the number of electrons in subshells. Before that, we have to know that how many electron can be filled in each main energy levels. Main energy levels. For K shell, it has been filled by 2 electrons. Only 2 electrons can be filled in K shell, which is the first energy level. And for L shell, 8 electrons can be filled. For the third energy level M, 18 electrons can be filled in the third energy level L. For the M shell, 32 electrons can be filled. Okay. Now look at the table. Shell number is given 1, 2, 3, 4, K, L, M, N respectively. Maximum number of electrons that can be accommodated in each level. For first shell, which is K shell, there are 2 electrons can be filled in the K shell. For shell number 2, which is the L shell, 8 electrons can be filled in the L shell. For the third shell number, which is M shell, 18 electrons can be filled in the third electronic energy level. For the last or M electronic energy level, 32 electrons can be filled. Then the subshells. Second row is subshell. For the subshell, 1s. Only 1s electron is available. These 2 electrons can be filled in the 1s electron, because S can be filled 2 electrons. In S sub-energy level, 2 electrons can be filled. Now, for the shell number 2, 8 electrons are in the second energy level. That means 2s and 2p. Why not 1s and 1p? That's because this is the second energy level. So we have to denote as 2s and 2p. In the first sub-energy level, 2s, we can fill only 2 electrons. In case of the second sub-energy level, which is 2p, we can fill 6 electrons in the sub-energy level. Now, in the case of third energy level, which is M shell, there are 3s, 3p, 3d. There are 3 sub-energy levels. The first and the maximum number of electrons that can be accommodated in that shell is 18. So we have to fill the 18 electron in these 3 orbitals. In these sub-energy levels, the first 2 electrons can be filled in the 3s orbital, and the second 6 electrons can be filled in the 3p orbital, and the final 10th electron can be filled in the 3d orbital. And for the fourth shell number, or n shell, there are 32 electrons are available. So we have to fill the 32 electrons in the 4 sub-energy levels, which is 4s, 4p, 4d and 4f. So we have to fill first 2 electrons in the first subshell 4s. In the second subshell 4p, we have to fill 6 electrons. For the third 4d orbital, we have to fill 10 electrons, and the final 14 electron can be accommodated in the 4f sub-energy level. We should know the maximum number of electrons that can be accommodated in each subshell, which is, for a subshell there are 2 electrons can be filled. In case of P subshell, maximum number of electrons that can be accommodated is 6. For D subshell, maximum number of electrons can be accommodated is 10. For the F subshell, 14 electrons can be filled. Okay. Then how to fill these electrons in each energy levels, each sub-energy levels? The electrons are filled in the shells in the increasing order of their energy. For example, the electronic configuration of carbon is 2, 4. For carbon atom, the atomic number is 6 and the maximum number of electron could be 6. So the electronic configuration is 2, 4. From this picture, you can see that the carbon nucleus is shown in the green color, and to the nearest to the nucleus there is one energy level, and the first energy level, which is called K shell. This is the main energy level, and there are 2 electrons in the K shell because only 2 electrons can be accommodated in the K shell, and the remaining 4 electrons are arranged in the second energy level, which is called L shell. When the electrons in an atom are distributed in subshells, they are filled in the increasing order of their energy. This is called sub-electronic configuration, subshell electronic configuration. As we discussed earlier, the number of electrons in an atom is equal to its atomic number. Atomic number is denoted by Z. For example, the subshell electronic configuration of hydrogen is 1. That is, atomic number of hydrogen is 1. So, how many electrons are present? There are only 1 electron is present in the hydrogen atom. The next question is, in which shell electron is filled? In case of main energy level, the only 1 electron of the hydrogen atom is filled in the K shell, which is the first energy level. From this picture you can see that in which subshell is filled. K shell has only 1 subshell, which is 1s. So the first electron can be filled in, the only 1 electron can be filled in the 1s orbital of the K shell. The subshell electronic configuration of hydrogen can be represented as 1s1. So simple. Okay, well, here's a small assessment for you, my students. There are a few questions given below. Just read it. How many electrons are present in helium? The atomic number of helium is 2. This is the hint. Atomic number of helium is 2. Then how many electrons are present in helium? As we said earlier, the atomic number of an atom is equal to its electrons. Number of electrons. Okay, the next question is, write the subshell electronic configuration of helium. Okay, and the third question is, write subshell electronic configuration of beryllium. And the fourth question is, write subshell electronic configuration of boron. And the last question is, write subshell electronic configuration of carbon. I'll give you some hint. For beryllium, boron and carbon, the atomic number is 4, 5, 6 respectively. When we write the subshell wise electronic configuration, the number on the left side of the subshell denote the shell number, and the number of the top right side denote the number of electrons. For example, look at the table. Here is the subshell electronic configuration is written 1s2, 2s2, 2p3. For the 1s2, consider 1s2 only. Then the leftmost one is the shell number of that electron, and for the 2, the top right 2 is the maximum number of electron can be accommodated in that subshell. Okay, now look at the table. First one is nitrogen element. Its atomic number is 7. Total number of electron is 7 because the element atomic number is equal to the number of electrons. And we can write the subshell electronic configuration as 1s2, 2s2, 2p3. Why 2p3? This is because there are 3 electrons are available. All other 4 electrons are filled in the 1s2 and 2s2 already. So the remaining 3 electrons are filling in the p orbital. The p orbital is vacant because it has capacity to fill maximum number of 6 electrons. So it has vacancy to fill more electrons. In case of fluorine, the atomic number is 9. So the number of electron can be accommodated is also 9. And the subshell electronic configuration is 1s2, 2s2, 2p5. For sodium, the electronic configuration is 1s2, 2s2, 2p6, 3s1 because the number of electron is 11. And for argon, 18 number of electrons are there because the atomic number is 18, and the subshell electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6. From the subshell electronic configuration of argon, you can see that all the subenergy levels are completely filled. This is why all the noble gases are stable, because they are completely filled. They are non-reactive. Here you can see the graphical representation of relationship between the subshells and their energies. In the x-axis, the main energy levels are given K, L, M, N, etc. And the y-axis energy is plotted. You can see that the first subenergy level 1s has lower energy than the second subenergy levels 2s and 2p. But in case of 3s, 3p, 3d, the 2s, 2p has lowest energy. In case of 4s, 4p, all the 1s, 2s, 2p, 3s, 3p, 3d are lower than 4s, 4p in case of energy level. But in case of, while comparing 2s and 2p, 2p has more energy than 2s. In case of 3s, 3p, 3d, the highest energy level is D, 3d. And the second highest is 3p. And the lowest energy level is 3s. But in case of 4s and 4p, 4s is not higher than 3d in case of energy. 4s is lying in between 3p and 3d. And all other energy levels, comparing to all other energy levels, 4p is the highest energy level. So the subshell electronic configuration in case of increasing order of their energy is, look at the picture, just look at the picture and you can find it. The first lowest energy level is 1, then 2s, then 2p, 2p less than 3s, less than 3p. Then here is the peculiarity. Here after 3p there is no 3d. In between 3p and 3d there is 4s, because 4s has lower energy than 3d. So after 3p the 4s subshell can be filled according to the increasing order of their energy level. Then after 4s 3d subshell can be filled, and after all 4p subshell can be filled. So we can write it 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d less than 4p. Here is a simple method for learning the increasing order of energy levels. From this picture you can see that first we are arranging all the sub-energy level in according to the increasing order of the shell number. See that first one 1s, then 2s 2p, then 3s 3p 3d, and then 4s 4p 4d 4f, then 5s 5p 5d 5f, 6s 6p 6d 6f. You can write more. Now first we are drawing these arrows to indicate the energy levels. So you can find the first energy level should be 1s, then 2s, then 2p 3s, then 3p 4s, then 3d 4p 5s, then 4d 5p 6s, likewise. Okay, this is the diagonal rule for electron filling order. The electronic configuration of scantium is 2892. Here you can see the atomic model of scantium is given right to the text. The first electrons are filled in the K shell, and all other electrons are filled in the L, M, N shells according to the increasing order of their energy. Then how can we write subshell electronic configuration for scantium? Electrons are filled in the subshell for scantium is in the order 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d1. But this is written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1 and 4s2. Why? Based on the increasing order of energy, once the 4s is filled, the next electron is gone to the 3d orbital. This is how scantium gets the electronic configuration 2892. While writing the subshell electronic configuration of elements with higher atomic numbers, the symbol of the noble gas preceding that element may be shown within square brackets, followed by the electronic configuration of the remaining subshells. Got it? The electronic configuration of potassium. This is an example. The electronic configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. The preceding noble gas argon. The preceding noble gas is argon. Argon has the atomic electronic configuration 1s2, 2s2, 2p6, 3s2 and 3p6. As we learned earlier, argon are completely filled. Hence we may write the configuration of potassium using the symbol of argon as given below. In square bracket we have to write argon, AR. Symbol of argon is AR, and 4s1, because the remaining shell is 4s1. All other are filled in the argon, configuration of argon. For more convenience, some examples are given here. For the scantium, atomic number of scantium is 21. We can write the subshell electronic configuration as, in square bracket we can write AR, and after 3d1 and 4s2. For calcium, its atomic number is 20. The preceding noble gas is argon, so we can write argon Ar in the square brackets. After that we can write the 4s2 subshell. Likewise, you have to do all other highest molecules, highest atoms. There are some peculiarities in the electronic configuration of copper and chromium. Let's see. For copper, the subshell electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. But the stable configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s1. In case of chromium, just look at the electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. But this is not the actual electronic configuration. The stable configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. The changes is lying in the 3d5 and 4s1. For copper, changes are lying in the 3d10 and 4s1. For the subshell electronic configuration of chromium and copper, the configurations with half filled D shell or completely filled D subshell show greater stability. That's why they have the peculiarities of their electronic configuration. Okay, well, we are going to wrapping up today's session. See you soon with a new topic. Thank you. Thank you for watching.